Today we're going to start section 11.2, which is titled Curves, Polygons, and Symmetry. And we're going to take a look, again, a lot of vocab in this section. Some things that are going to be very familiar to you, others that may not be quite as familiar to you. And again, kids identifying shapes is occurring at earlier and earlier ages. Lots of two-dimensional and three-dimensional shapes that even my first grader is expected now to know. She was showing me very excitedly the other day she can draw a cube now. It's very exciting. She's got a little ways to go before it really looks like a cube, but she's definitely on the right track. All right, so to start with, the description of what actually a curve is. A curve is an object similar to a line that is drawn inside of a plane. The easiest way to think of this is a path drawn on paper. So it doesn't have to be curvy even to be considered a curve. A line segment would be considered a curve with this definition. Connected means that you have a curve that can be drawn without lifting a pencil, i.e. there are no breaks in the figure. There's no stopping and restarting in another spot. And a curve is called simple if it does not cross itself. Okay, so what we're going to do, I've got one more definition, I guess it didn't get put on this page, over here. Well, one more that specifically applies to what we're talking about. I'm going to flip back to those pictures here in just a second. Closed is the last one I wanted to talk about. Closed means it's a curve that has the same starting and stopping point. Okay, so I'm going to go back to where those shapes were. Obviously, I should shift that definition a little bit. I probably just was out of space. Have 4 pictures here I'd like for you to sketch on your paper if they're not already there. I don't think they are. Are they? They are. Okay. When I did my notes, whenever these notes were created, they weren't in there. So great. What we're going to do is we're going to identify which of these descriptions the curves here satisfy. So all 4 of these are curves. By the definition, it's a path from one place to another place. They're curves. We're going to identify whether they're connected, simple, or closed. So we're just going to say whether they are or they are not. So is this curve connected? Yeah, I mean, you don't have to pick up your pencil to draw anything, right? So it's connected, so we're just going to write connected next to it, or under it, or whatever you want to do. How about simple? Is it simple? Yes, because it doesn't cross itself. And is it closed? The definition was over here. Is it closed? No. So it is not closed. How about the second shape? Connected. Yes. Simple. Yes. Closed. Yes, this one is also closed. How about the next one? Is it connected? Yes. Is it simple? Yes. Is it closed? Yes. And our last one, is it connected? Yes. Is it simple? No. It is not simple. Remember, simple means it doesn't sort of cross over itself, and this one does. Is it closed? Yes. So these 3 definitions can occur independently of one another. They can be true or not true and still talk about them being curves. A polygon is a simple closed curve, so it fits all those descriptions, but its sides are line segments. And 2 line segment sides meet at a point, and that point is called a vertex. So these are all polygons. There's 5 of them here. We will learn and talk more about identifying more specific names for these polygons as we continue. But they are all polygons because they fit that description. They're all simple, they're all closed, they're all connected, right? They are all line segment sides, and yeah, so they fit all the definitional criterion. Convex. A shape is convex if its curve is simple and closed, and its interior contains any segment between 2 points on the curve. And I'll show you what that means in terms of a picture here just a second. If it's concave, it means it's simple and closed, and it's not convex. So concave really just means not convex, which must mean it fails to satisfy that last description where it's talking about this interior thing. So let me show you from just the first two pictures what it means by that last description. So if I were to take this point here on this sort of worm shape, and I were to take this point here on the worm shape, and I were to connect them, what you will notice is that I go outside of the shape in order to form the line segment connection, right? That's exactly what cannot happen by the description on concave at the beginning. I'm sorry, convex at the beginning. Said the wrong one. You can't do that. So if it does that, it's concave. One way to think about that is that you could imagine, hang on, let me get this piece removed, this sort of portion of the graph or the curve looking a little bit like a cave in the sense that there's an alcove there, a hiding place, right? Where you can't be seen around some of the corners, but you're still on the outside of the actual shape. Now, if you do the same thing with this second shape that I've got here, the second figure, you'll notice that this doesn't happen, right? No matter what 2 points I pick on the curve itself, if I connect them with a line segment, I am completely inside of the shape still. So if I have the ability to do that for every pair of points, right? Like I can do that for some of the points over here. I'll just draw two of them here. Those two are connected, right, inside of the shape. That does not make it convex. Just because I can connect them, I have to be able to connect all of them like that in order for this to work. And that works for my second shape here, but it doesn't work for the first one, right? No matter what 2 points I pick here, even if they're really close, they're still inside of my shape. So this one right here, the second image, which is a polygon, is actually convex. How about the third one? What do you think? It is concave. And to justify that, you have to be able to connect 2 points and be outside the shape, and we are. So yeah, that's a problem. And the last one, convex or concave? Yep, that one is convex. All right, so far so good? All right, so let's go back to that idea of polygons, and we're going to talk about ways to categorize or classify them by the number of sides, or you can talk about the number of vertices that they have. This is a collection of 8 names. They aren't the only names, but they're the first 8 names, and after this they are less common, so you probably won't remember or think of them as quickly. So we have a triangle, it's 3-sided shape. A quadrilateral is a 4-sided shape. A pentagon is a 5-sided shape. Hexagon has 6. Heptagon is one that we don't hear used very frequently, so that might not be one that's super familiar to you, but it's heptagon. 8, octagon. You see those all the time, right? Your stop signs. 9 is a nonagon. And 10 is a decagon. When we name a polygon, like we say polygon and we call it something, we label it by its vertices in order. And it can start anywhere and it just goes around the shape. So there's not a specific location that we have to start listing them, but we do have to list all of them. So it's pentagon A, B, C, D, E. But you could likewise say, if that were the right order, pentagon B, C, D, E, A, and it would be okay. Or reverse, E, D, C, B, A. You can go backwards very well, obviously. All right, so it's just going in order left to right around the shape. A diagonal is any line of a polygon connecting non-consecutive vertices of the polygon. So what's the shape of this one over here, this polygon, ABCD? With the, yeah, it's a quadrilateral, right? These are our only options to choose from right now. Quadrilateral has 4 sides. So on this one, there are only 2 diagonals. There's diagonal AC, because A is connected to B and D by line segments. So AC is a diagonal, and BD is a diagonal as well. But the more sides your shape has, the more, not always like consecutively, but you will have more diagonals. So I'm going to flip back over here real quick just to show you that same shapes that we had before. All these are polygons. Let's just take the one here in the middle. I think it's got 10 sides. So if you imagine this one right here, and we're talking about, we'll start with this vertice that's here at the top. It actually has diagonals that can be drawn to every other vertice besides the ones it's next to. So just the diagonals from that vertice alone would be all of these. And that's not all the diagonals. I can do that from every single vertice. I can draw diagonals out. So you can see if you have a decagon, you've got a lot of diagonals, right? It's also interesting because like a triangle has no diagonals. So there is a relationship for how many diagonals you will have, and I think we'll see that a little bit later. But generally speaking, more sides means more diagonals. So let's talk a little bit about angles of polygons. We have 2 different general types of angles, interior and exterior. An interior angle is sometimes just called an angle. It's an angle of a convex polygon determined by 2 sides having a common vertex. So in this diagram that's drawn here, is this diagram on your paper? Fabulous. In this diagram here, it's all those little alphas on the inside, the ones that look like they're not shaded in. Alpha 1, alpha 2, all the way to alpha 5. Those are all interior angles. They're inside the shape, okay? And then exterior angles are a little different. So notice the exterior angle is not like right here all the way around. It doesn't do that. That's not the exterior angle. So be real careful that you're not thinking that. An exterior angle is an angle that is formed by one of the sides of the polygon. So if I'm looking at this one right here, it's this side of the polygon. And then it is the other side extended out. So this is the other side, but then you extend it out. That wasn't good. And it creates that blue angle beta 1, and that's an exterior angle. So you might notice that alpha 1 and beta 1, as they're drawn here, they form a line, right? When you connect them together the way that they're drawn, they're actually lying alongside a straight angle or a line. And that's how they will always work. So let's talk about the word congruent. Specifically here as it references segments. Congruent segments are 2 segments of exactly the same length. The symbol looks like a tilde on top of an equal sign. That symbol is used to indicate that segments are congruent. We like to use the word equal sometimes when we really mean congruent. So if I correct you, just know that that's a normal tendency that you have, and I understand it. But the word equal actually means that the 2 segments have the same size and shape and location. Like they're exactly the same segment. That's what equal actually means. Whereas congruent just means they're the same length. If two segments are marked with the same number of hash marks, they're understood to have the same length. So you can see in this picture right here that there's little blue hash marks marking AB and CD. That means that they're the same length. You'll typically just use one hash mark like that unless you have a diagram where there's more than that going on, and you might need to show that two pairs of things are the same length, right? So these two are the same length and they have hash marks that are just one, and these two over here have double hash marks because they're two, they're not the same as the other ones, but they're the same as each other. Okay, along the lines of this idea of congruent segments is the idea of congruent angles. Very similar in terms of the definition. So congruent angles are two angles that have the same measure. Same symbol. That symbol means congruent. So if you put that symbol between angles, then it means that the angles are the same size. So if I'm looking at this diagram, ignore my next piece, I'm not quite there yet, and I want to talk about congruent. The diagram actually shows, let me mark them, these two to have one hash mark each, right? So these two angles over here, marked with one hash mark, are equal in size. So what that means, if I were writing out, is that angle BAF, I'll just start from the top and go around, BAF is congruent to angle FAC. Okay, and that's what it would look like. Those are congruent angles. Now, again, we don't say that the angles are equal. They're not equal. But what you'll see noted in the next blank right here is that it has a little M in front of it. Do you guys see that? That M means measure of. It's a way of saying, I'm not really talking about the angles, I'm talking about how big they are. So if I have that notation, it is appropriate to put an equal sign between them, because that notation M in front of it means it's only talking about how big it is. So that's an alternate way of discussing it where you do use an equal sign. The measure of an angle, in this case DAE, is equal to the measure of angle EAB. Two angles marked with the same number of arcs, or whose arcs have the same number of hash marks, are understood to be congruent. And this is what I was talking about on the previous slide, is that you see two hash marks on the part where I just sort of circled or boxed in red, and then, you see one on each of them, and over here in the purple one you have two hash marks on each of those angles. And that's making sure that you understand that, for instance, this angle out here is not congruent to the angle over here just because they happen to be marked, but they're marked differently. So it's a way to mark the diagram, but to be clear about what we're trying to say. All right, equiangular. Equiangular means that you have a convex polygon where all of the interior angles are congruent. One that's very familiar to you that's equiangular would be a square or even a rectangle. All of the angles have the same measure. Equilateral means that all the side lengths are equal. And if a shape is both equiangular and equilateral, then it's called regular. And a square is regular. It's equal angles and equal sides. It is a regular quadrilateral. So we have the ability of drawing, not necessarily because we're good at drawing, but it exists to have a regular shape of all of the different types of polygons. We can have a regular triangle. It's an equilateral, equiangular triangle, right? Like we know that one familiar. Square. Square is an equilateral and equiangular quadrilateral. It's a regular shape. The pentagon that you see drawn right here below, that's a regular shape. That's one that's probably fairly familiar to you. It's not the only way you can draw a pentagon, by the way, right? But it's the one where all the sides and angles are the same. A hexagon, the one that's on there, that other one, that's a hexagon, and it has equal angles and equal sides, so it's a regular hexagon. Again, I can draw a hexagon differently. I can sort of elongate it and make it look really long and skinny. I could even do that and preserve the ability for the angles to stay the same, but not preserve the ability for the sides to stay the same. So you can distort things and not necessarily distort both at the same time as well. All right, so what we're going to do next is we're going to draw some shapes. And I'd like to pause and give you a chance to actually do something without me just talking at you. So your goal on number 1 and number 2 is to draw the shapes that are described. After you've had a chance to do that, I'd like you to turn to somebody nearby and kind of just look in and see if you agree that their diagrams doesn't have to match yours, but just agree whether or not their diagram hits those marks, like does it do what it says, and have them do the same for you. And then if you need to make adjustments, you can. So we'll take a couple of minutes to do that, and then we'll come back and see what kind of shapes that you came up with, okay? So take a couple of minutes and find shapes, or try to find a shape of each of these descriptions. All right, so everybody's kind of stopped talking, so you must have had a chance to at least discuss it and come up with some ideas. What did you draw, if you can verbalize it anyway, on number 1? Rectangle. A rectangle is probably our easiest thing to draw with that description. Certainly not the only thing, but a rectangle will certainly work. What did you draw on number 2? Equilateral triangle doesn't work because equilateral always means equiangular. It's the only shape that you can't manipulate in one way or other. It's kind of weird. You drew a pentagon. So you drew it kind of like the shape over here, but you just you raised the roof, right? Yeah, of course. Okay, so let me try and draw that. No promises on it looking convincing, but if I continue these up a little further, wow, that was bad. Something like that. If I drew it well, it would work. What else did you guys draw on that one? Yeah. A diamond. Yeah, and that actually has a name. We haven't talked about it yet, but it's called a rhombus. That's its mathematical name. So, yep, a rhombus is your smallest shape that'll do that. So this one would be equilateral, but not equiangular. Oh, and I think I drew this. This one is actually what I meant to draw up here. My bad. Elizabeth, I think you might have wanted me to draw something like this. Does that sound better? Yeah. There we go, because now all the sides are the same, or at least they could be. We'll pretend like they are, and if I mark them, then they have to be, right? Absolutely. Yeah, so all those sides are the same, but the angles are definitely not in this one. So there's lots of shapes you could draw that will do these things. These are just a couple of options in each category. Cool. All right, let's try to get through the next page. Again, a lot more vocabulary, and then we'll stop for today. I feel like all the stuff here in chapter 11 at the beginning especially is just me talking a lot, and I'm sorry boring you about that. But all right, some polygons that are common polygons. Specifically, we're going to talk about triangles first. So a triangle can be classified by its angles. There's 3 different categories of triangles when you classify them this way. Acute, right, and obtuse. An acute triangle has 3 acute angles. And that's the first picture. All of those angles are acute, and acute means less than 90. And then a right triangle has exactly 1 right angle. Notice its other 2 angles are acute. Okay, so they've all got acute angles. It's just how many of them they have, really. So the right triangle has 2 acute angles, but it has a right angle as well. And then our obtuse triangle has 1 angle that's obtuse. And again, obtuse means bigger than 90. And you can see that that obtuse angle, at least the triangle drawn here, would be down here. So there's that angle that's bigger than 90. The other 2 are still, again, acute. So we've got at least 2 acute angles all the time. That's not the only way we can classify our triangles. Another way to classify them is by their side lengths. So we've already mentioned equilateral, but it is a way to classify them. If you have 3 sides that are all equal for a triangle, that's an equilateral triangle. And by the way it's constructed, it also happens to be equiangular. The second one is an isosceles triangle. An isosceles triangle has two congruent sides. And then the last one you'll see is not marked on any of its sides at all, and that is a scalene triangle. It has no congruent sides. They're all different. Another common polygon that we have are quadrilaterals. So I already mentioned one of these a moment ago since it was brought up, and here's a few others. So the first one that's mentioned here is a trapezoid, and this is something to be aware of. A trapezoid is a quadrilateral with one or two pairs of parallel sides. This is a little fuzzy because it depends on the resources that you use. Some resources will say that a trapezoid has only one pair of parallel sides. If it has two pairs of parallel sides, it's got another name. And it does have another name, but it won't categorize that as a trapezoid. And some resources will. So it just depends on what materials you're using as to how it categorizes that. So we're going to keep our options open at the moment since we don't know what you're going to be experiencing with the curriculums that you're given to use. So the first shape, that's actually all the shapes that are drawn here, are trapezoids. So an isosceles trapezoid specifically is a trapezoid with the base angles congruent. So the one that's here in the middle is an isosceles trapezoid. It means that those base angles are the same. Notice neither of the other two have that feature. So sometimes they're isosceles, sometimes they're not. Now, the reason that it's really not necessary to call something a trapezoid when it has two pair of parallel sides, as I mentioned before, is that it does have another name. If you do have two pair of parallel sides, it's actually a shape called a parallelogram. So a parallelogram is a quadrilateral in which both pairs of opposite sides are parallel. Parallelograms almost look like a rectangle that's been sort of slanted, right? That's the image that we sort of have in our mind, and the slant is the same slant amount on the left as it is on the right? This is exactly the problem that my daughter was having when she was trying to draw her cube, is she couldn't get her sides to slant at the same angle, so nothing was looking quite right in her cube that she was drawing. A rhombus also has the ability, the description, a rhombus, that the opposite sides are parallel. Like that happens, but it's also true in a rhombus that the sides are the same length. So it's got sort of an extra condition on top. It's a parallelogram with all four equal sides. So we saw a rhombus before when I drew it over here when we were talking about it, and some kids will, sometimes we will call it a diamond. You'll see that as a sort of, I don't know, what's the word I'm looking for? A common vernacular kind of a word to use for this. But it's actually called a rhombus, mathematically speaking. And so you can see the shapes that are right here actually fit these categories. This one would just be a parallelogram. It's clearly not a rhombus because it's got a longer top and bottom than the sides. You can see it, right? The way this one's drawn, if it were marked anyway, it's very easily convincible that this is actually a rhombus. But that doesn't make it not a parallelogram. It's also a parallelogram. It's just that description isn't quite as specific, right? It doesn't give you as much information as calling it a rhombus does. Our next shape, actually, you have probably a better name you'd think of using. What would you like to call this? Looks like a rectangle, right? Like we aren't like marked with the corners and everything, but it looks like a rectangle. But at the very least, you can see that it also has the same description that we can call it a parallelogram, right? Opposite sides are parallel. So rectangles are parallelograms. They just are. The last one is also a parallelogram. I can't get it all fit in there. And again, it looks convincing enough, and your book will have marks if it should be, that we would say, yeah, that might in fact be a rhombus. Kind of like this one looks convincing enough that these are probably right angles, and it's probably a rectangle specifically as well. So this one we would call a rhombus too. All right, so what we're going to do is we're going to pause right there. We will pick up on, I think it's page 5 with rectangle. Actually, let me at least say the rectangle one because I already drew the picture. Rectangle, let's just do rectangle. I know it's on the top of your page, but rectangle and square. The rectangle and squares are parallelograms with right angles. So we have that same shape that I had on the previous slide where I had a parallelogram, but I have a right angle to it right here. So a parallelogram is going to have a right angle, then it's a rectangle, and then a square will be having it's a rectangle, so it's got the same features. It's got the right angle and it's parallelogram, but it's also got equal side lengths. So we have these marked here too. So this one would be a square. Notice it's interesting because it's a square, but it's also a rectangle. You can also call it a rhombus. You can also call it a parallelogram. That says gram at the end. And actually, since we have that super sort of vague description, you could call it a trapezoid the way that we describe trapezoids. So square is its most informative name, but it fits all the other definitions also. So it's a very interesting situation, and we'll talk more about the other pieces of what's going on here and pick up with kites next time.